with 5 different hospitals, and which particularly we are working on gastric. So these are the contents of today's talk. As I mentioned before that, I'm working on gastric cancer and breast cancer. These two cancers are very prominent specifically in East Asian countries like China, Korea, and other countries. And we are we're working on this project. So whole slide imaging. In traditional way of diagnosing the cancer, in old days people used to diagnose the cancer while using some microscope images. Under the microscope, the cancer was diagnosed. But with the latest technologies like whole slide imaging, in which we digitize the slides, the tissue is taken from the organ of the body. It may be gastric, it may be kidney, it may be breast, or some other part of your tissue that is taken from the body, and it is digitized on the slide, and it can be stored on computers. Previously, this was not happening like that. The tissues were taken, but that was stored on paraffin blocks, and to manage and to store the tissues were very challenging. But with the advent of new technology like whole slide imaging, it has been transferred and stored and organized with computers. So this technology provides some facility to apply AI techniques for the diagnosis of the cancer. And when we digitize the whole slide, there are different magnification level of the slides. Here you can see 40x, 20x, 10x, and 5x. These are the different magnification level of the whole slide image. Whole slide image is not a common image, just like we deal with, for example, an image is consisting of maybe 256 by 256 size or 416 by 416 size. Anyway, the point is that the image size is very small. But in this case, when you digitize the slides, the size becomes very big, and it is more than 40, even 20 GBs as well. I will show an example in later slides. So there are high quality, high resolution scanners. Using these scanners, we digitize the slides and we store them, and we apply different kind of AI techniques, and we process it. So here I have shown that the traditional way of pathology and the latest way of pathology. In previous, in the old days, tissue were taken and they were stored in the paraffin block storage. And this is not the physical way, not good way to store and to analyze the tissues, because after some times the quality of the tissue decreases and the diagnosis cannot be up to the mark. And also one of the drawback of the diagnosis of the tissues were only under the microscope we can analyze the cancers. For example, if the pathologist is not well abreast of the diagnosis process, if his knowledge is not up to the mark, so the diagnosis may be different, and he may diagnose wrongly. So if we use whole slide imaging, and in whole slide image we can store on the computers and we can analyze it while using different kind of technique, and different pathologists remotely can access those whole slide images, and they can present their views on the diagnosis of the cancer. But in this case, only limited. For example, if the cancer is, the patient is reported in some center, for example, only limited number of pathologists can analyze the cancer here in this case. But if we use whole slide imaging, then remotely we can access, for example, pathologists from across the world can access those slides and analyze the cancer. While in our project, while sitting here, we are accessing the server of those hospitals, and we are using those slides and we are using for our research purpose. This is big advantage of whole slide imaging. If we have only the microscopic tissues, then we cannot access those remotely, as you know that. So this technology, whole slide imaging technology, enabled to apply AI techniques as well, and using latest AI techniques we can diagnose the cancers with high performance. Here these are the scanners. There are different kind of scanners. While using the scanners we scan the whole slide. So this is one example of whole slide image. You can see here the size of the image is 21.2 GB. This is our real data we took from the hospitals. For example, this is the name of the hospital and this is the idea of that hospital. So you can imagine 21 GB. If you watch a movie, it is maybe 2 GB of 2 hours movie, maybe 2 GB or 1.5 GB. But here in this case you can see 21 GB is size, and the width and the height you can see here 169,319 is width is this, and the height is 44,000 something. So to deal with this whole slide imaging is also very challenging. So problem statement: since WSI are categorized by their extremely high resolution, often 40,000 into 40,000 pixels, is I just shown you that how big it was. So it requires high computing machines, GPUs and storage. Currently we are working on our servers. We have 4 servers. We are working on those servers. We cannot use although we can use in our local machines, but there are so many limitations to use whole slide in our local machines. Therefore we are using our servers. Four servers we have, and we work on servers. One limitation is that it needs high quality and high performing computing machines. The other limitation is that WSI is very big. Either we have to downsample to process, to apply AI techniques on the whole slides, or make patches of these whole slide. Make patches. Patches means to divide this whole slide into smaller patches of 256 by 256, 416 by 416, according to your need. Because when you apply CNN architecture or any deep learning architecture, you cannot directly give this whole slide, which is big in size, 40,000 into 40,000 pixel size. We cannot directly give it to the architecture, AI architecture or deep learning architecture or CNN architecture. So we need to apply some pre-processing on it. If you downsample it, for example, if you downsample it and we squeeze the whole slide, in that case there are some problems. Your substantial loss of detailed information. The detailed information related to the cancer may be lost, and ultimately at the end the accuracy of the model will be low. For example, if there is a cancer in the whole slide, and because of the downsampling, at the end the model predicts that there is no cancer, in that case there will be disaster. So this is not a good solution. Downsampling is not a good solution. So the other solution is make patching. Okay, we have a big slide, we make patches of 256 or any other size which any CNN architecture can take directly. So we make patches. Okay, here there are different patches, but there is also a limitation if we make pages, what will be the level of this page? What will be, this is the whole slide. This is the big image, and we make different pages. If we make pages, then we don't know what will be the level of this page, or what will be the level of this page. In that case, the pathologists need to annotate those areas. For example, this area is cancer, this area is benign, this is normal, and this is other. So in one whole slide, there may be different annotation of the slides. Okay, when we make this annotation, because as we mentioned before that whole slide is very big, to manually annotate, this is very time consuming and labor intensive, and also it is very expensive. So the manual annotation is also very challenging. And one of the other problem is that the shortage of pathologists worldwide. I have mentioned some figures here. You can check here. For example, in China, there is an estimated shortage of 90,000 pathologists. So this is also a limitation of whole slide imaging diagnosis. So what is our motivation and objective? So to address these problems statements, we have presented self-supervised foundation models and weakly supervised approaches with great potential in pathology-aided diagnosis. So to enhance the accuracy, to enhance the performance, we have used foundation model. This helped us to increase the performance of the model. And for the annotation problem, for the manual annotation of the problem, we have used weakly supervised approach. This is one of the technique which is very popular in pathology. And in pathology, multiple instance learning is an approach, weakly supervised approach, which enable us to apply to diagnose the cancer without having the tightly labels of the whole slide images. So the objective is to develop an efficient AI model with high accuracy and performance. For this one, we have used foundation model. And to develop an AI model that mitigates the annotation challenges associated with WSI, we have used weakly supervised multiple instance learning technique. So as I mentioned before that we were working with the pathologist and 5 different hospitals in Korea. So for my research, I have used 2 kind of data sets. This is private and this is related to gastric cancer. Another one is breast cancer, and this is publicly available. In here, we are doing metastasis and non-metastasis classification, and also PDWMD classification. Here are some details of metastasis, lymph node metastasis. Total we have used 4,168 slides, whole slide images, not normal slide. And training 3,334, validation and testing, you can see here. And these are the information of the hospitals. We have 5 different hospitals: Severance, Danwood, Invencha, and Kenya. And this is for another task, that is PD and WMD classification. We have used 346 whole slide images. In this one, why we are using a limited number of, for example, in previous case we were using 4,000, around 4,000, or even we have used 5,000 slides. But here we only use 346. Why? Because in this case they have annotated. Based on the annotation, we have categorized, we have used these slides. Therefore, the number of slides in PD-WMD cases is low. Here we have public dataset description. 2 kinds of dataset we have used, Camion 16 and 17. And the total number of slides for Camion 16 is 339 and for 17 is 414. So foundation model and weakly supervised learning method. So coming to the foundation model, what is foundation model? Actually, foundation model is kind of technique in AI in which we use self-supervised learning, and we use a plethora of data. A massive amount of data is needed for foundation model to develop. It doesn't need any kind of labeling of the data. Just we give the data to the model, and the model itself learns the intrinsic features, and it categorizes different kind of objects by itself. So to develop this foundation model, we need massive amount of data. It is not possible with limited amount of data. People are using millions of data for developing foundation models. And in digital pathology, this is very trendy nowadays. Even in Stanford, in Harvard, and some big research centers, they are using this foundation model. So digital pathology foundation model is a large-scale pre-trained AI model that has been trained on vast amount of pathology data. This is very important because to develop domain-specific foundation model is very important. Nowadays, everyone, for example, if I read some papers, mostly people are going towards to develop, for example, CT scan based foundation model, X-ray image based foundation model. In our case, digital pathology based foundation model, domain specific. Previously, people using the transfer learning techniques. For example, if we use ResNet or VGG, those transfer learning techniques are based on ImageNet. ImageNet consisting of natural images, and if we use those transfer learnings for extracting the features, although they give good result, but because they are trained on natural images, they don't give high quality performance. If we use domain specific foundation model, the accuracy and the performance will be enhanced. So therefore we aim to use pathology based foundation model in our research, and we applied in our scenario, and we got the results. So the importance of foundation model in pathology: improved diagnostic accuracy, as I mentioned, and also scalability and weak supervision. These are the some important features of foundation model. Here you can see different types of foundation model. We have language foundation model, we have vision foundation model, we have bioinformatics foundation model, and we have multimodal foundation model. Then coming to weakly supervised learning method. This is one of the technique in which models learn from data where data has partial, loosely, noisy or indirect labels. The labels are not tightly with specific patches. There are loosely labels or indirectly labels or noisy labels. So leveraging this technique, we are using it for the automatic annotation of whole slide images. In weakly supervised learning, we are using CLAM, that is clustering constraint attention multiple instance learning processes, analyze large number of whole slide images quickly and efficiently, and interpretable method for data efficient whole slide image classification. We not only use this technique, this is one of MIL, for example, multiple instance learning. We have tried different other MIL techniques as well. For example, SimCLR, we also used DTFD, we also use MRAN, but we came to the conclusion that this technique is faster compared to other techniques. When we were using, for example, MRAN, it took maybe 7 days, 5 days, depending on the number of slides we use. And we are also using SimCLR dual stream network as well, in which when we were training the data, it took more than 2 weeks for the training of the model. So this was one of the best approach we found, and we tried in our research. This is the architecture of our study. We have whole slide image, then we make the segmentation of the tissue. We extract only the tissue area from the whole slide. After that, we applied some pre-processing, for example, conversion of color space from RGB to HSV, and also we did some smoothing counters and also removing the artifacts from the data, and we made pages of whole slide images to 256 by 256. After that, we gave the whole slide, for example, this is the one page from this whole slide. The size of this image is 256 by 256. We gave it to our self-supervised foundation model, where we create two views, view 1 and view 2, and this is based on self-distillation, in which we have two networks, teacher network and student network. And we masked some part from this, the global, it has the global view. The teacher network has the global view, and the student network has also two views, but some of the areas are masked, so that this student network tries to mimic and tries to translate this part on the teacher network, and it learns from the network. And at the end, we have two kinds of laws: the reconstruction laws and the alignment laws. And at the end, we got high quality features of 1024 features we extracted from this foundation model. After that, this is our foundation model part. After getting the high quality features, we gave it to our weekly supervised learning architecture, where training took place. And we have attention-based network, attention-based bone network, in which we have the attention score for each page. Based on the attention score, there is a grading, and there is the ranking of each page, and make some clusters, positive and negative clusters. And this is the interpretation and visualization part of our architecture. For example, if we give a whole slide image, it detects and it finds out the highest score pages in the whole slide and give it a red color. In coming slides, I will show how our model did the prediction. So these are the results for PTWMD. Previously, we were using weekly supervised learning, which is based on simple weekly supervised learning, which is based on ImageNet. While using ImageNet architecture, we extract the features and we train our weekly supervised model, and we got the accuracy of 84.99 for this PTWMD classification. When we integrate our foundation model, which is solely trained on digital pathology images, whole slide images, because this is domain specific. Therefore, what it did, it abruptly increased the accuracy of our model from 84 to 90. And we also notice in metastasis classification, non-meta and meta. When we apply traditional and simple weekly supervised learning, the accuracy was 76. But when we integrate our foundation model, we got 81.81. This is the 10-4 cross validation, and here you can see this is our whole slide image, the actual whole slide image, and this is the prediction from our model. The red areas are the metastasis part or non-metastasis part, and the blue area having low attention score, maybe normal or other kind of cancer, or it may be normal. Here you can see the ground truth for this slide is meta, and the prediction is also meta. And we also have shown that the probability of meta and non-meta. For meta, the probability was 0.99, and for non-meta, you can see. This is another slide for non-meta. The ground truth is non-meta, and the prediction is also non-meta, and the probability is 0.99. We also applied, for example, make different data sets for each hospital. We have present the results here. You can see. This is the attention map for PDWMD classification. Here you can see this has been annotated by the pathologist. This slide, this is the whole slide, actual whole slide, annotated by the pathologist. Pathologist said that this is PD area, this area is PD area, and this is the prediction from our model. Look how it correlates and how it has complete consent with the pathologist. For example, this area has been annotated by the pathologist, and our model also predicted this is the PD. And in every slide you can see here, the red part is showing PD here. And this is for the WMD. This has been annotated by the pathologist. Here you can see our model has also predicted like this in the visualization part. And these results are for Chameleon 16 and 17. This is for simple weakly supervised, and this is the integration of from 87 to 98. You can see from 88 to 97. This is 10 for class validation. This is for 17, and this is the attention map for 16 and 17. You can see here. And we also compared with the previous works. For example, previously for claim it was AUC was 92. This is also self-supervised plus weakly supervised. They have 91, but in our case we are getting 90, 97 and 98. All the techniques having low score. So conclusion. In this research study, we introduced an integration of foundation model and multi-instance learning based weakly supervised approach for classification of gastric and breast cancer. The proposed approach is efficient and computationally fast. This model doesn't require any kind of annotation for WSI classification as we shown here. And this approach will expedite the diagnostic process of cancer while beefing it up and reduce the mortality and morbidity rate of cancer patients.
For example, if we were taking from ImageNet, we were using the
some weights.
This architecture.
Yeah.
When we say the weight of, we use the weight of the unit,
Mm-hmm.
and for feature extraction we use the VN transfer.
Mm-hmm.
So in this technique, how we can say we use the unimodal for in this case we use the unimodal for feature extraction, and what's the difference? We use the weight of the unit.
Okay. Normally, when you do some feature extraction while using ImageNet, what you do?